This is the introduction part of our presentation on the topic thermoelectric energy harvesting. Beside, we can see the outline of the presentation, where we are going to see why thermoelectric energy harvesting. Then we are going to see what is it. We are going to see the component of thermoelectric energy harvesting, and then we are going to see the operation of the energy harvesting. Then finally, we are going to explore some of its applications. First of all, why thermoelectric energy harvesting? Actually, what triggered the attention of researchers towards exploring this energy harvesting? The answer to this comes from the demand for battery alternative. As we can see from the figure, which is an IoT analysis, that the number of connected IoT devices is estimated to reach 39 billion in 2030. Just from now to 2030, which is just 5 years, there is high tendency that the devices they are going to reach almost 30 billion. So how will producing a battery to this system be? Then secondly, apart from this one, there are other factors to be considered in terms of the need for a battery alternative, like design constraint, because in system most at times battery occupies the largest part of the system. Then what is thermoelectric energy harvesting? From the word, as we can see, thermoelectric. Thermo means heat, electric means electricity. It just conversion from heat to electricity. From the definition, as we can see, is the process of converting temperature difference into electrical energy. What happened from the figure, as we can see, here we have the hot side and here we have the cold side. So the migration of the energy from the hot side to the cold side is what generates the electricity. And then it is of two types. There is the one that has the source heat as the source, and there's the one that has the cold as the source. So in this one is the heat that migrates to the cold side, whereas in this one is the cold that migrates to the heat side. Then, while the theoretical background of this energy harvesting, as we can see from this figure, it is made by two pieces of semiconductor, which is made from bismuth telluride. This is the compound of the system. This p-type is doped with an impurity acceptor, while this n-type is doped with donor acceptor. As we can see, there is a thin copper linking the p-type and n-type together. But in reality, these two pieces of semiconductor cannot generate electricity. That is why there is a need for we to have series and parallel of these devices together in order to have a tangible electricity in order to power our devices. So as we can see how the connection is. This one is connected to this side, P to N, N to P, P to N, N to P. And finally, this is the positive terminal and this is the negative terminal of this system in order to have the
So these are the components of thermoelectric energy harvesting. Part of there are three major components. So you have the heat source, which is the hot side, can be any surface that is hotter than the surrounding. We also have the thermoelectric module, which is the generator. It's like the heart of the system. It contains the P-type and the N-type, which has been explained by my colleague on how it works. Then you also have the heat sink, which is to keep the other side cooler than the hot side. So that way you will be able to make sure that there's always one side that is hotter than the other side. If not, your thermoelectric harvesting will not work. So this is like the block diagram. You have your heat source, you have your thermoelectric generator, and then you have your heat sink. So you also have an electric circuit, which is as you see, we have the load, you have the load management, you also have like the boost converters and voltage regulators, because the voltage generated by Your generator might be too little, and then you also have a capacitor which stores your energy. You have your charge management, like your battery management, and then you have fault and protection so that you can ensure flawless execution. So the basic example or application which we are discussing is the batteryless IoT sensing using thermoelectric energy harvesting from industrial motor waste heat. So the problem or the reason for implementing this application is the problem, which is what conventional systems need battery replacements and they require higher maintenance costs. So previous works also focus on partial IoT subsystems prototypes only, while the main contribution of this application is what to develop a thermoelectric energy harvesting from the heat of industrial motors. We all know. So the moment you have one motor on one side and you have a cooling system on the other side, you can be able to generate energy. The second contribution of this application is to implement IoT sensing system without battery. So it charges autonomously using the energy generated, and then to demonstrate a reliable sensing system with cloud data transmission in reality, which my colleagues will be able to give more deeper explanation as to how this process works. Thank you.
Moving on to the application of thermoelectric energy harvesting, we will look at this example, batteryless IoT sensing from industrial motor waste heat. This system is designed for predictive maintenance in factories. As shown in the diagram, it consists of two separate main parts: the thermoelectric generator assembly and the IoT node. In this setup, the waste heat from Bosch motor is transferred to Maro TEG using an aluminum plate as a hot side. The cold side is maintained by the Wakefield heatsink, which receives the airflow from the motor's own cooling fan. This creates the temperature difference required to generate electricity from the motor's operation. Next is the IoT node. This node uses a DC-DC converter to boost the low output from the generator and change a 20 mF capacitor to supply the sensing system. A microcontroller is used to control the system and process data from the sensors. This data is then transmitted through a long-range protocol via a LoFa transceiver. Two other components, an op-amp and buck converter, are included to monitor the capacitor voltage and provide a stable voltage for the MCU and transceiver. This allows the system to remain fully operational without any batteries.
These are the overall circuit level diagram. Start from a motor to the transceiver connection. After data transmission is complete, IoT node is in sleep mode for 20 seconds to reduce inactive energy consumed. At the same time, the recharge of the capacitor is processed for the next energy harvesting. The measurement of all electrical data is done by the AQ, or the acquisition adapter. The figure A is the measurement method during the energy harvest, especially focused on the power output of the generator, and figure B is the measurement of the harvest and voltage supply from capacitor to the IoT nodes. The figure above shows the characteristic of the practical harvester system. A thermal difference reaches its steady state around 5 degrees Celsius before it drops down. Voltage and power output of the generator are about 81.5 millivolts and 4.19 milliwatts at steady state, which both can reach its maximum of 89.6 millivolts and 5.07 milliwatts. Oh, from the previous slide, the temperature difference with the only load connection is around 5 degrees Celsius when IoT node is connected to the generator instead. So the heat gradient should not exceed than 5. The capacitor voltage performs as a sawtooth graph due to the change of sleep and recharge mode after the data is completely transmitted, as you can see from the data transmission pattern below. So the final outcome, the harvest energy of 6.17 joule, is sufficiently provided for IoT sensing, which consumes energy only 6.05 joule.